So work is one of those terms, and there's a couple in physics that the definition of the term doesn't necessarily give you a great idea of what it is. I guess you could say it's vague. It's just something that kind of, it's a way to just define something, but it doesn't do a great job of doing it. We'll see that again with momentum. It's not necessarily the definition is not necessarily a great definition. It's just kind of what it is. So work, very simply, is just, oops, wrong color. We don't want that color. Work is just force, a parallel force times the distance that it travels, right? And by distance, it's actually mean displacement. Okay? So work, very simply, they say it in that review packet, is just the dot product of force and displacement. Without going too far into what dot products are and cross products are, dot product means that it's a scalar, meaning the direction doesn't matter. Okay? Cross products it does, and you do things a little differently. It has to do with matrices. All right? So when you apply a force on an object and you cause its displacement to change, you're doing work. Does that make sense? Okay? So when you do work when you apply a force and its displacement changes. Now what if I took a box, right, and I pushed it along the ground to one place, and then I pushed it back to the original place that it started? Would I do work? Did or didn't? Did I do work? Yes or no? Right, I did no work. Why did I do no work?
Because there's no displacement.
Right, there's zero displacement.
But if
okay.
If you split that up into two, then you would...
Yeah, we're talking the total path,
like
right?
Overall you did no work, but like in the two separate actions.
Correct.
Okay.
Right. But think of it this way. You were positive work going one direction, you did negative work coming back. Right. Okay? So, this parallel piece is very important. Think about it this way. If I'm talking displacement in the x direction, if I lift this book up, am I doing any work? If we're talking about in the displacement in the x direction, do I do work? Right? I'm not doing any work. So in this case, right, the displacement is zero even though there's force. Another, in the book, they give it an example of the person picks up a suitcase, right? Yeah. And they walk with it this way, right? And they say there's no work done. Why?
Because the force is being applied in the direct and displacement.
Right, so, for those of us that speak English, the force is being applied up, correct? The force is being applied up while the displacement is going to the left or to the right, correct? Very badly. So, so the important thing, and when we're doing work, the force needs to be parallel to the displacement. That's why I put this little parallel symbol here. If we look at a box, right, and we apply a force this way, right, and we have some angle theta right here, that then means that the part that is going to be doing work is going to be this f sub x. And if we look at it in terms of this triangle, right, this is the adjacent side of our triangle. So we could say work is then equal to f cosine theta times our displacement. Okay? So now, let's see if we can, we've got a force in there, right? We've got F. So let's see if we can make some sort of relationship between work and like Newton's second law. All right, let's see if we can put those two together and what do we get out of that? All right? So I know work equals F times X, right? Force times displacement. And I know F equals ma. All right? When I do this, if I make this substitution, I know that work then is equal to ma times X. Okay? Now, I want to get some sort of relationship out of this. we see that if we're going to have something accelerating, it's going to be moving, correct? Right? And so I can use a kinematic equation to get things in a little more useful terms. Okay? Okay? So if I look at AX, do we have an equation that has AX in it, or think of it like AD? Yep.
Velocity minus squared equals initial velocity squared plus v times v acceleration.
Yeah, so we know that v sub f squared minus v sub o squared equals 2AD, right? Or in this case, we'll just call it AX. Right? So if we make a quick move here, we've got v sub f squared minus v sub o squared over 2 is equal to AX. Okay? If I take that and I plug it in here, I get that W then is equal to m v sub f squared minus v sub o squared over 2. And if I make a if I just push this all through, I get that 1/2 m v sub f squared minus 1/2 m v sub o squared is equal to work. Okay.
Alright. I saw that equation in the book and it's like
Now, this 1/2 mv squared, clearly it's kind of important because it shows up twice here, right? It's the term for kinetic energy. Okay. Now, kinetic energy is equal to 1/2 m v squared. So for kinetic energy, we call it capital K. All right? Kinetic energy is the energy because of an object's motion. So when it's moving, you have kinetic energy. The greater the speed, the greater the energy. Right? If it's not moving, we don't have any kinetic energy. Here's an important thing, and this goes back to the unit we did on kinematics. Remember when we had like 1/2 AT squared? Right? We squared the time, and they asked like the distance, and it wasn't like double. It was like it was a square of it. Right? So it was like typically 4 times as much. Okay. Same thing here. If I'm comparing speeds, right? If one is twice as fast as the other, the one that's twice as fast has 4 times as much energy because of this squared term in here. Okay, so that's something to keep in mind. I guarantee just because of the nature of questions, you'll see questions like that where an object is twice as fast compared to another object. How much more energy does it have? Right? You'll see questions like that. And then if they talk about masses, then double the mass just means double the energy. Okay? So we can say, if we put these in here, does this look like this is K sub F, this is K sub O, right? Or more simply, it's just delta K, right? The change in the kinetic energy. Right? So when we do work on an object, we're changing its speed. It's essentially what we're seeing right here, correct? When we do work, so if we apply a force and we cause this displacement to change, we're causing its speed to change. Right? This is one of the versions of what's called the work energy theorem. Right? Work is in joules. This should kind of give you a hint the relationship. Work is in the unit joules. Energy is in the unit joules. So they're together. Right? They're married. Right? You kind of think of work as the ability to use energy, to create energy. Okay? Does that make sense? And we're not really creating energy. I guess we're transferring it, we're manipulating it, we're redistributing it. It's kind of really more what it's saying. Okay? So we can see that, again, when we do work, we change the amount of energy that an object has. Okay? So that could be for anything, up and down, left and right, whatever thing we're talking about. Let's say now we're just going to apply work, we're going to do work on an object so that it changes its position in the y direction. Okay? So we have then, again, work is equal to force times displacement. Right? And if we talk about lifting something, right, is the force that we lift it with constant speed, is that equal to mg? Right? If we're lifting an object at a constant speed, is it?
Yeah.
It's right. We're applying a force of mg to it. Okay. And the last thing I'm going to do is I'm going to say we're not really dealing with x per se, right? Because we're moving now in the vertical direction. So instead of calling it x, I'm going to call it h, the height that it changes. Okay? So when I do that, I get a few things. I get w, now the f's, right, equal to mg, and now the displacement is going to be the height that it moves. Okay? Where the height is the difference between the two y positions. Okay? And if we think about if one h is 0 and the other h is some new h sub f, right, we get two terms. We really get then w is equal to mgh final minus mgh initial. Okay? This mgh term, and this is what always screws, one of the things in physics that doesn't make sense, okay, along with massless strings and pulleys, is, you know, kinetic energy, we use K, right? When we're talking potential energy, we don't use P, right? We use U, right? So potential energy, and this is the thing that's a little off too, and we'll talk about this in a second. Potential energy, now, we'll get into it now. Potential energy is think of it as the ability to do work. It's stored energy. So work is, right, energy is the ability to do work. Potential energy is stored energy. In this case, the mgh, right, that is gravitational potential energy. Gravitational. Yeah, probably. Okay? So, if we look here, we get that work is equal to the change in potential energy. Okay? Now, kinetic energy is kinetic energy, right? It's just the, energy an object has because of its motion, right? Potential energy is stored energy, and we can store energy in many different ways. We've got stored energy in, right, the gravitational, right, the ability to do work, right? If it falls, it's changing its displacement, so we're doing work, okay? Chemical energy is stored energy, right? Until we break those chemical bonds, and then the energy is released, right? If we're talking about a spring, and this is one that you'll see, right? If we're talking PE of a spring, right, then U is equal to 1/2 K x squared, right? So I might call it U sub S, and I might call this U sub G, right? So depending on what we're talking about, potential energy may have different forms, right? So if we have a spring, like something that's bouncing up and down on a spring this way, we're going to have kinetic energy, we'll have some potential energy, we'll have probably some gravitational and some spring potential energy in there, okay? Because all those things are doing some work, okay? So does that make sense? We're good so far? So what we can say then, because we have work, now if we look here, we have work is equal to the change in kinetic energy, correct? Right? Well, we also have work is equal to the change in potential energy. But what happens is if I get one type of energy, I lose it from another place. Right? So we can call it negative delta K equals delta U. Now if I expand that out, I get negative K sub F minus K sub I equals U sub F minus U sub I. Okay. So then, doing the work, doing the algebra, I should get then K sub I plus U sub I is equal to K sub F plus U sub F. Okay. And this will do a lot of work for you. This is the law of conservation of energy right here. And this says that, you've probably heard things like, energy cannot be created or destroyed, right? That's essentially what this is saying, is that Any energy that you start with, whether it's kinetic or potential, has to equal the energy, kinetic or potential, that you finish with. They may be distributed differently in terms of how much kinetic and potential you have, but the sum of them has to be the same. Okay? And if we throw in a little extra piece, if we think about an external system, right? This will keep you. If you think about a system, this will usually work. But if you have something else happen, so let's say you have a little cart and it rolls down the hill, you can look at the energy. But if then you come outside, so you're outside the system and you apply a force to it, right? You're doing work on it, then you have to add that work term as well. So that the work that you do plus the initial energy is equal to the final amounts of energy. That's if a force outside of the system is being applied. Okay. So if it's just a car or a ball rolling down a hill or a roller coaster or something like that, there's no outside force. But if I run up and push the ball with a cart, I'm outside the system of the cart. Therefore, I have changed the energy of it because I have taken some of my energy and I've applied it to the car. Okay? Does that make sense? Okay?